Hello everyone, and welcome to today's energy storage news webinar with Envision on the UK's long-term 2029 tenders and the future of grid stability. I'm Andy Colthorpe, Editor of Energy Storage News and Deputy Editor-in-Chief for Publishing at Solar Media. Today's webinar focuses on a topic that the global industry is gradually beginning to recognise: the need for low-carbon sources to provide system stability services that have been traditionally played by thermal generation assets. As the term strongly implies, these services, which include inertia and short-circuit ratio, are necessary for the stable functioning of the electricity grid. Their requirements rise when more inverter-based variable renewable energy is added to the system, and at the same time, the retirement of fossil fuel generation also means fewer turbines spinning constantly to provide the rotating mass essential to maintain grid stability.
The differentiator for Envision, and I promise that's my last slide on Envision, is that we are fully integrated BESS provider. So from cells to software to PCS and DC and AC systems, all developed in-house. That's just not a feature that is here to look pretty on a slide. It has real life advantages. And to make an example, in the context of grid forming, one of the key elements is overload capability of current to provide inertia. And we can look at this in a holistic fashion, from DC overload current on the batteries to AC overload current of the PCS. So this integrated approach from cells over software to overall hardware offers the advantage that we can look at these applications from end to end. Now, what is it about grid forming? Why it is even needed, right? Okay, we want to phase out thermal generation. That's a noble goal, but what is it, right? And one of the examples that we can look at is a recent event in Europe. This is the Iberian blackout on the 28th of April. I personally was in Spain that day. It's quite an interesting experience to have a 12-hour blackout. Interesting things start to happen. So it's something to take serious, I would say, at least. And when you look at the cause of this event in Iberia, it's similar at a high level to all these kind of events and outages. It's a cascade and multiple factors going together. So I think the official conclusion is on the slide here. So it's a combination of technical, structural, and managerial factors, and ultimately the end was because of a voltage surge that then was out of bounds. So what can grid forming do? Grid forming can, of course, not prevent managerial errors, right? That will never be the case. But what grid forming does, it provides stability and robustness then if you time. So instead of a couple of seconds, maybe you have half a minute or a minute of time to react, to bring the system back into a stable zone. And that time is really, really valuable to a system operator in Spain, but of course also to somebody like NISO in the UK. That's why they are willing to pay for this robustness and stability. If you look at more concrete, what has been the technical causes in Spain? So we have overvoltage. That's something grid forming can help with in terms of voltage regulation with reactive power and other elements we'll see in detail. We have a rapid frequency drop, so high rock-off event. Of course, that's somewhere where virtual inertia based on grid forming technology can play a role. And then, of course, it is important because as we move to higher penetration of renewables, in this example, 59% solar and 12% wind, so similar situations as in high windy days in the UK, obviously with a bit less share of sun, but that's exactly when grid forming can help. So in context of this event, right, I'm not sure grid forming BESS would have prevented the Iberian blackout, but it would have provided time, and it could have helped with the concrete symptoms of frequency decline and voltage surge and oscillations. So now, enough from me. At Envision, we take pride in our deep expertise and in our capable R&D employees and engineers. So with that, I would like to hand over to our grid forming expert, Dr. Lu, who's going to speak a bit more in detail of how we realize grid forming and what are the challenges associated with it.
Okay, thank you, Michael. I'm Xiaodong. I'm the control engineer in Envision Energy behind grid forming. It's my great pleasure today to introduce our understanding on grid forming and stability pathfinder. First, please allow me to briefly introduce my understanding on grid forming to make sure everyone is on the same page. So I bring up two pictures on the right side. One is grid following, one is grid forming. As we know, grid following is a power source. It's controlled as a power source. The inverter frequency always follow the grid frequency by using the phase lock loop. And grid forming we control as a voltage source. And the inverter frequency is established by mimicking the mechanical moment of inertia of the synchronous generator. And there are different grid forming control methods. The most popular one is droop and a virtual synchronous generator. Here in Envision, we are using the VSG control. The reason we use it because we want every critical parameter to have a clear meaning of a physical meaning. So talk about the application scenarios. Grid following, for sure, it could be applied to the strong grid. And when it's applied to the weak grid, the capability is limited, especially when the short circuit ratio is less than 2. And grid forming, we can use it in strong grid, weak grid, or off grid. And oops, sorry. Oh. Okay, so sorry, there's the sequence is a bit different, but it doesn't matter. Let me try to briefly introduce our how we design the grid forming. Here, our control design is based on the MATLAB Simulink, but we verify the grid forming using the PSCAD EMT simulation. We also provide the dig silent and the PSSE simulation for system analysis. And after the design and simulation, we also do the hardware in loop verification. We have 3 hardware in loop platform in-house. The most popular one, Typhoon, ArchiLab, and RTDS, both in-house. And here, before when we do the grid forming design, we do the investigation. We do the investigation of the global grid forming specifications. We learn from the UK Stability Pathfinder. We also did the investigation from Australia, from Germany, and from the US, and of course from China. And based on our investigation, the UK Stability Pathfinder is the leading specification on grid forming. Even in the Stability Pathfinder Phase 3, it listed all the detailed test cases on the stability on the grid forming specifications. Here is what I summarized from the Phase 3 compliant note. I categorized their requirement into 3 categories. The first one is inertia to the rock-off, inertia to the phase jump. And the second one is reactive power support to the voltage event. Voltage event include the short circuit event, temporary overvoltage, and multiple events. And of course, it also includes the fast current limitation for the grid forming, because grid forming is a voltage source, and it is one critical challenge to the grid forming control. And the third one is Australian oscillation damping to both frequency and voltage. So after the design and the investigation of the specifications here, and also verifications by using the hardware in loop and simulation, here is what we tested on site. We built the largest grid forming test platform. It is a 5.5 PCS set, including 2 PCS in parallel. And there's also a battery pack of 40 megawatts hour connected on the DC side. And the whole setup was built in Inner Mongolia. And the grid fault is generated by using a grid simulator. reached power 5.5 megawatts as well. We used the grid simulator to simulate different grid faults like rock-off, phase jump, and voltage fault and oscillation. We also used the grid simulator as the load to test our setup in the islanding mode. By using this whole platform, we test and verified our grid forming base there for 6 months. We had more than 200 stability pathfinder cases verified on site and witnessed by some customers. And we also verified the grid forming cases and certificated by China State Grid, more than 1,000 cases there. And I mean, although we see that UK Pathfinder is the most advanced one in the world, but in the China China grid forming specification, there's some even more stringent requirement, like the zero voltage right through. We do the zero voltage right through there for 10 seconds, and inject reactive current for 300%. Okay, that's the test, and here I have some field test results listed here for demonstration. The first one is the voltage events or short circuit level, including both low voltage right through and high voltage right through. The second one is, and the third one belongs to the inertia. Inertia response to the rock-off, inertia response to the phase jump and phase angle jump. And the fourth one is oscillation damping. And besides specified by the stability pathfinder, we also did the black start and the islanding test on site. And there's also some results demonstration here. So the first one is low voltage and high voltage right through. We did the zero voltage right through for 140 milliseconds, following the specification from Pathfinder, and it's followed by high voltage right through. The maximum we done is 130%, and we even do the 3 repeated low voltage right through plus high voltage right through, as shown on the top right. You can see that the current is limited within the limits, and we are using the virtual impedance to do the current limitation. And you can also see there's no oscillation or instability during or after the continuous grid voltage fault. And the second result is about the inertial response. We test on site the maximum rock-off of 2 Hertz per second. And you can see the result on the right side. We also have some dashed line there to make sure the inertial power injected matches the calculated value. We also verified the inertial response time, especially the initiation time, by using the scope. Yeah, the third one is about the phase angle jump. We did the test on site to do the inertial response to phase angle jump up to 60 degrees. And we verified the initiation response initiation time. It also help us to verify the current limitation, because the phase angle jump is most challenging to the current limitation. So we can see the effect of the virtual impedance current limitation. We can also see the PWM blocking when the current limitation is limited by the software. Yeah, this one is about the oscillation damping. We did both oscillation damping to frequency oscillation, oscillation damping to voltage oscillation. And we did the test from 0.1 Hertz up to 3 Hertz, while in the requirement, it is from 0.3 up to 2 Hertz. And we also did the verification there to make sure the active power or reactive power provided by our grid forming base is anti-phase. We also introduced an equation here to make sure we really provided the damping power. Yeah, the last one is about black start. As I mentioned just now, we have 2 units parallel. So on site, we also did the soft start or black start of the parallel units. And the ramping time is less than 30 seconds. when we look at the figure on the bottom left, you can see there's a single green line, but actually there are two lines almost overlap each other while the control is distributed. We also tested the parallel operation of in the aligning mode, as I shown on the right side. It's black start and black stop, and also black start with aligning operation with ramping load. Yeah, that's pretty much for the results demonstration. And besides that, after we got the data from on-site, we also use it to verify our control design in the simulation. And as it's shown here, it's verified that our simulation matches the field result very well. Let me switch to the Stability Pathfinder Long-Term 2029. This spring, when Long-Term 2029 was released, we did the investigation and realized that there's not much difference between Stability Pathfinder 3 and the Long-Term 2029. And all the differences are listed here, and some of the critical bullet points I highlighted here. The first one is regarding the inertia constant. Now the maximum inertia constant is 25 seconds. But when we review the design, our design is also compliant with it. And the other control functionality was not influenced by this configuration. And the second critical one is the fast fault current injection. Previously in phase 3, it was the fault current was evaluated at 100 milliseconds after the 3-phase fault, but now it's evaluated 40 milliseconds after the 3-phase fault. And we also did a review on our field test result, and it missed the requirement even before without any optimization. I will show you the data later. And the third major difference is the reactive power mode. Previously, the grid forming BESS, especially for the grid forming BESS plant, it's required to work in either target voltage or constant reactive power mode. Now it's only changed to target voltage. Constant reactive power mode is no longer required. It makes sense since grid forming BESS is a voltage source. It helps to stabilize the voltage. And the last but not least one is the fast current reinjection. Previously, only the minimum value was specified in the specification, but now the minimum value and the maximum value are both specified. So we need to make sure our current is between the black line and the red line on the left figure. Yeah, as I mentioned just now, after the investigation, we did a review of all our test data on site. And here is the one critical part of it, the reactive current injection. Now it's required to be 40 milliseconds after the 3-phase fault. So if we look at the figure on the right, and the reactive current is on the bottom right, IQ EMT means IQ in simulation, and IQ field means the field test. We got the test data we got. You can see that after the 3-phase fault occurs at the time of 3 seconds, we have the response time of IQ to be less than 30 milliseconds. And the settling time is around 40 milliseconds. So it means that even with our original control design, it meets the requirement very well. Okay, that's pretty much for my introduction on the grid forming Stability Pathfinder part. Yeah, we can exchange later on other technical points. Now I would like to introduce my colleague Sai, who is the black start expert, to introduce his understanding on the restoration service.
Thank you, Xiaodong, for your technical insights on the GFM and stability requirements for the UK market. Hello, everyone. I'm Sai, Senior Engineer System Integration from Envision. So today I'm going to run through in detail the restoration service requirements of LT2029. So as part of the NISO technical requirements, so there are two types of restoration services. Like one is the primary restoration service, which is the anchor generator, and the other one is a contractual top-up service. So what's the difference between an anchor generator and a top-up service? So for the anchor generator, it's basically we are going to restore the system without any external voltage reference from the grid. Whereas on the top-up service, we are going to restore the system, the best system, by taking the reference from an adjacent anchor generator or a power island system. Just for a simple analogy for everyone to understand. So the anchor generator is like you are just lighting the first candle, whereas the contractual top-up service, it's like you are lighting new candles with the first candle. So, and the requirements which you see in the slide are very brief ones, and I hope most of you would have read through in detail the technical requirements in the information shared in the NISO website. And if some of you, if you have not seen it, you can download the technical requirements from the NISO website and go through in detail. I'll move on to the next slide. So in this slide, basically, I'm going to explain about the black start sequence on how like we are going to use as a BESS as an anchor generator or a primary service provider. So in a typical condition, this is like a bottom-up approach. Like basically, we are going to energize the grid from zero, and so so when we need to operate the BESS as anchor generator is when there is a blackout condition on the grid, and uh, like if everything is like isolated and open. So when there is a blackout, basically your BESS system is going to shut down on the loss of mains, and all your substation and everything will be in a de-energized state, and you will be in islanded. So that's where when the NISO will uh, instruct us to perform the restoration services. So before the NISO instruct us to perform the restoration, the first thing what we need to ensure is like we have sufficient backup supply to feed all our critical loads in the AC and our basically the PCS and the batteries. And it's not only about the PCS and batteries, like we have also have so many auxiliary systems and switch gears and like control systems, the plant EMS, SCADA. So all these are very critical for us to perform the black start or self start. And so once we have the auxiliary supplies, backup auxiliary supplies for all the PCS and all the critical equipments, and so we'll wait for the instruction from NISO, and then we do perform the black start. So during the black start is basically like we will engage the battery racks to provide the DC voltage to charge the DC bus on the PCS. And we are going to start the PCS in like a soft energization or a soft start mode, and then we energize the transformers, and basically we are going to uh, close or energize the dead bus. So once we energize the part of the net's transmission system, then we'll start engaging the load breakers, and then like you would need the PCS to respond to the voltage and the frequency fluctuations depending on the load blocks. And so you usually as part of the net's transmission system, there could be various anchor generators part of the network. And so when initially NISO is requesting us to perform the primary restoration service. Like they will instruct us every unit independently, and then at some point of time we need to synchronize all these systems. So for synchronizing, it's important that there should be a synchronizing breaker uh, where we verify the voltage, frequency, and phase angle and synchronize uh, the anchor generator units. In typically, you will be having lots of technical challenges, and uh, there are so we have also have solutions to how to mitigate these risks. So the first risk is obviously the transformer inrush current limit. So current limitation. So like basically we have the soft start capability on the PCS so that we ramp the voltage from 0 to the nominal in a slow method, so that we can limit the interest current of the transformer. And we also have got like super grid transformers on the substation side. So and like so basically we can use the point of a switching device to close the breakers when there is zero current. And then obviously we have like over voltage issues, and so the BCS is capable should be capable of handling these over voltage issues. So that is how we size the PCS to handle this reactive capability of the system. And so as explained by Shadang earlier, like we have got oscillations in the from the grid. So the PCS should be capable of having the damping function, and we have got filters in the PCS to uh, tune the harmonics of the system. And so once we have energized the transmission system, like basically we go in a staged block loading. So the main thing we need to ensure is like we have sufficient uh, energy in the batteries to provide the block load for the required duration. And there are like certain minimum duration which needs to be met uh, by the BESS system while participating in the restoration services. So these are some of the operation challenges that need to be resolved during the operation phase. And in general, like the operation sequencing. This like we will verify as part of the system studies during the project delivery phase. and and here we are going to follow a top up like bottom down approach, and all this also will be validated through the EMT and HIL test. And I can say that like from Envision, like we have addressed fully addressed all these technical challenges, and we have validated this in our system validation center at Ordos in Inner Mongolia. And so the next slide, I'm going to talk about the top-up services. So unlike anchor generator, the top-up service is not complex. Uh, so for the top-up service, it can be either like a top-down approach or a bottom-up approach. So usually, if it's a top-down approach, basically we are going to get the so when there is a typical blackout in the system, so there will be an anchor generator plant which will be adjacent to the plant or a unit which is providing only the top-up service. So the anchor provider will be providing us the external voltage reference or the auxiliary supply from an islanded bus, or we can use the backup supply from the plant to restart all our auxiliary systems to be ready for the black start. And uh, so basically, the substation will be energized by the anchor, and using that voltage or frequency reference, we can start the BESS in grid following mode. and we can operate in parallel, or like we can also operate as a GFM. Basically, we can do the self start and we can energize till like a medium voltage substation, and then we can synchronize with the external grid. So, and there is like certain durations that needs to be met as part of the LT2029, and so those are mentioned in detail in the document from NISO. So so the technical challenges for the top-up service. So again, this is not a very complex compared to the anchor, like but however, this also needs to be planned in a proper way during the like design phase of the project, like how we are going to meet these requirements while operating the best system as a top-up service. So the synchronization part is a key thing, like how we synchronize with other systems in the transmission network. And the load sharing is like when we are operating in GFL, it is relatively like it's going to be we need to tune the PQ curves in the system, whereas in grid forming, so we have to tune the VF droop curve in a way that we share the load depending on the capacity of the systems. And then the reactive power, it's less complex, and like we just follow the Q group hierarchy, and the ramping, and these are all some challenges which can be easily managed in the systems, and also the protection and stability, I think. So I'll go on to the next slide. So in this slide, I just want to show you like on a unit level to get an whole picture, like how do we do the black start sequence via an external power supply. So we have got like transmission grid, substation, auxiliary transformers, the emergency backup system, and the PCS with the best transformer, and then the DC blocks, battery DC blocks. So when typically you can follow the numbering sequence, like when a blackout happens, usually the grid fails and the best shutdown, and like the next thing you would need immediately, like all the systems will be running in a UPS backup in their individual equipments, but however, like that will be for a specified duration, and you would need a more like an emergency backup also, like if if we don't receive the instruction from the NISO within 2 hours, so then probably we would need like an emergency backup supply, because they can ask us to connect or restore the system within the duration of like 2 to 72 hours. So the auxiliary backup is one of the key things, like on how we design the system, and either we can use the diesel generator or like a small inverter, backup inverter, which we take the DC source from the batteries and feed the in-house auxiliary loads. And with this, we will get all the critical loads fed from the emergency system, and then we start engaging the DC rack contactors of the battery racks, and then the DC bus will be charged, and the PCS will need to be will need to start in the grid forming mode, providing the voltage and frequency reference. And again, we energize the transformer, and then which will in turn energize the substation, and basically we restore the whole some part of the net's transmission system. Yeah. So thank you, everyone. Thank you for this opportunity, and I'll hand over to Michael for the conclusion. Thanks.
Thank you very much, Say. I will make this brief because I see a lot of interesting questions coming in as well. But just to wrap it up, you know, I think you've heard it a couple of times, but UK really is leading from our perspective in terms of specifications, because it is so detailed in the grid code that is very valuable to us as a supplier. So we can really engineer against something and not just, you know, leave it in PowerPoint as we see today. It is also predictable in terms of revenue streams. Of course, you don't know how much you're going to get paid in an auction-based system, but once it's clear, it will remain the same for many years. So that gives clear technical specifications with predictable revenue streams, gives a good and strong investment signal. So we believe these two combinations will likely be followed by many markets around the world. As also Andy mentioned in the beginning, there's a couple of markets that go in a similar direction. Now, the reliable operation of a net zero energy system to certain degree will likely use grid forming PCS as a key element. I hope you also saw that grid forming is sort of a suite of stability services. It's a bit more than a checkbox exercise, right? Sometimes, people believe, okay, grid forming, yes, no, tick a box, or restoration, yes, no, tick a box. It's more than that. You need to look at the site engineering. You need to look at the requirements holistically. You need to look at requirements from NISO holistically so they can do the studies in a reliable way, which leads us to LT2029. It's obviously a major opportunity for UK BESS and players in the UK in battery storage. Has very stringent eligibility criteria. So it's important that the modeling is based on proper simulation and hardware in the loop and real life testing. And we believe that's exactly where Envision can provide value. With our experts, we can that have developed these grid forming algorithms and have aligned all of our performance with UK criteria. We can be the right partner to enable this modeling and this EMT modeling in a compliance with NISO to make sure the project is eligible and in the end does provide the stability services as required by the system. Thank you very much for listening, and I'm sure now we get a couple of exciting questions from Andy.
Excellent. Thank you so much, Michael, Dr. Xiaodong Liu, and Sai. Yeah, great presentation, and I can see that it has really resonated with the audience because there are lots of questions, and thankfully not questions from me, but yeah, from our lovely audience. I would say that you can still put questions for the speakers in now. It's to be honest, unlikely we'll be able to answer them live on this broadcast, but all the questions that are asked will be sent over to Envision, and Envision will be able to follow up that conversation in full offline. So there's still every incentive actually to ask your question, even if we may not, unfortunately, be able to tackle it online during this broadcast. Anyway, so question here from Anthony. So thank you for your question, Anthony. How would Envision's solution enable stacking of inertia and short circuit level? I.e., how does the short circuit level capability impact the inertia capability, and what is the overload capacity? So I don't know who wants to take that one on first, but yeah, so you've unmuted first, Michael, so maybe you take the first.
I'll start at a high level, and then I probably need some support by Xiaodong. So let's start first with overall capability in terms of overload. I think the first thing that needs to be done is sizing, right? It's not that inertia and short circuit level are only done with overload capability of inverters. Maybe you also want to choose a bigger inverter models, and a supplier like us, we have different types of sizing. So for example, we have 2.75, 3.45 and 5 MVA PCS that we can potentially use, and so you have already a sizing. And then the overload capability depends on the model, but in our case it's somewhere between 1.2 and 1.5 per unit that we can provide for these services and the specifications we see in the UK. Then in terms of stacking, we see quite compatible because it is very unlikely that at the same time you have a short circuit level and an inertia event. Actually, I don't really see how the inertia is still relevant in a short circuit event. So I think I would say that would take over, but maybe you have another view, Xiaodong, and want to go a bit in more detail between the conflict of the two applications.
Yeah, thanks, Michael. Yes, we provide the short overload capability at 2 levels. Unit level, we provide the overload capability to make sure the current limit is not easily triggered. because we are voltage source. If we trigger the current limit, I mean the control function would be limited. And we also provide the overload capability at the plant level. Plant level means we make sure our short circuit level and the inertia response meets the requirement of the system operator. So when we talk about the difference between short circuit level and inertia, short circuit level will mainly provide overcapability on the reactive power part or current part. So we just need to make sure all the AC related components need to be configured very well. But for the inertia, it's influenced on both AC part and DC part. So not only the AC needs to be configured overload, but also the DC. That's it from my side.
Excellent. Thank you for your expertise on that one. Sorry, and I'm just trying to order all of these questions because, as I say, there are a lot. So actually, the audience vote for top question or most popular question, I suppose, goes to this one from Syed. So Syed, thank you very much. And this is kind of about the impact on the life and health of a battery storage asset through doing short circuit level inertia support, all the system stability services. Because I think it's important to note that obviously the UK market, is very well known for the ability to stack revenues from multiple services. And some of those other services might be more demanding than short circuit level and inertia. And so it says, well, I understand these events only occur once in a while, but when they do happen, do they impact the state of health of battery storage systems?
Yeah, if I can take that one, it's a good question. Yeah, so I think Xiaodong alluded with two key concepts just before in his answer. So for short circuit level, it's mainly reactive power. So you mainly need to look at the AC components, right? The DC cells itself are not really affected. So you need to look at that your AC components are properly sized, and with the grid forming control, you limit at the right points in time. So lifetime of your AC components not impacted. So the really interesting case is inertia, because inertia does actually potentially stress the cells to a certain degree, because you have high currents for a short period of time during the provision of inertia. And this is where the benefits of an integrated R&D roadmap comes into play. So at Envision, these specifications or these short-term overloads have influenced this battery cell development. And as Envision, we can say, given the frequency and expectations for currents and the sizing of our system, there is no impact of these inertia events on the degradation curves and the SOH of a system operating in the UK market.
Sure, and I don't know if Xiaodong or Sai, you have any thoughts you want to add on that at all?
It also depends on the strength of the grid, because we try to do the analysis based on the Chinese market, but we realized the frequency was too stable for it to really influence the cycle life of the battery. But I mean, we are also collecting the data from the global market, thanks to our global team. And yeah, I mean, maybe next webinar we can bring up with some detailed data to see the influence to the batteries.
Excellent. Okay, thank you very much. And then we have another really popular question from Chem. So thank you very much for your question, Chem. Chem's actually asked a few questions, so I can see this is an important and an interesting topic for you, Chem. Thank you very much for your engagement. And I would like to actually focus on two of those, if I may, or if we may. So Chem says he doesn't see how battery storage can replace conventional units for restoration, given NESO ideally wants plants with the capability to run for 5 days. Should we start with that first and say restoration? Sounds like it could be one for you.
Sorry, Andy. Yeah, sorry, I was on mute. So basically, the resilience of the supply for the restoration services for the primary restoration services 10 hours is the minimum time which we need to meet as per the tender requirements.
I think there's an aspect to that question, of course, as well, that goes back to the revenue stack of the UK, right? As a primary provider, you will have, and also as a restoration provider, you will have at all times needing some energy in your batteries, right? You cannot provide restoration services if your battery is empty. Now, it's not on us to comment what that effect is. Ultimately, will depend how well these services are remunerated, how expensive batteries are, and how it looks in the revenue stack. But that's an operational question. Can you have certain capacity of batteries always charged and idle, and is it profitable in the overall business case?
Sure. And the other question from our prolific audience member, Chen, is around the competitive dynamic between, if it is a competitive dynamic between synchronous compensators or synchronous condensers and the grid forming battery storage systems. Are those equally well placed to meet the technical requirements? Is there a level playing field? I mean, I guess, the argument from the battery storage industry would be that battery systems are more versatile and can do lots of other things, as well as providing the services that synchronous condensers do. But yeah, what would be your view, guys? I don't know who wants to go for this one first.
Yeah, I would try to provide a really detailed feedback, because we did the analysis, the comparison between the synchronous condenser with the BESS, but I didn't find it with me. But I mean, the conclusion from our investigation was the performance of the BESS is better than the condenser. I mean, but right now in my mind, I can only recall that the primary frequency regulation, which is the condenser doesn't provide. And also, we also compared the short circuit level and also the inertial response. Even in these two comparisons, I mean, we can still see the better performance behaved by the grid forming BESS. But I'm sorry if today I can't really provide with detailed results.
Maybe to put a bit perspective, right? If you look at the Pathfinder results, the precursor additions, we've seen, sort of these two technologies competing to one another. And initially, in especially when it comes to short circuit, BESS usually was lesser ranked. And I think to this day, if you have a site with very, very high short circuit levels, there is, a question if short circuit condensers make sense or BESS, because you do have a lot of switch gear that you need to size for these high currents when you do it with BESS, right? So it becomes an economic question again, which is ultimately, I think, the question. I think both technologies can provide it. BESS can provide it surprisingly well, as you've just heard from Xiaodong, based on our analysis when it comes to really key performance parameters. But as you said, Andy, I think the key point is that BESS are more versatile. You do this as an additional service to have a fixed revenue stream in your revenue stack that is usually largely driven by things like arbitrage, but that are less, easy to find financing for.
Yeah, absolutely. I mean, I guess the thing is that ultimately the stability pathfinder and then now these tenders are a competitive process, right? So I guess whichever technology is best suited, both from a technical and economic level, to meet those needs is ultimately going to win out, I suppose. And I know that in Australia, there's a real look at whether it will be synchronous condensers or battery storage, or perhaps, it'll be a combination of both, depending on what fits best for which location and, which node of the grid, I guess. But yeah, it's an interesting question. Certainly, yeah, would be keen to look at some point into those details of Envision's research into that as well. That sounds really interesting, I think.
And just to finish, I mean, clients that are very that believe very strongly, best is going to win this. We have clients, who are building synchronous condensers, and we have clients we're speaking to who are developing co-located sites, best plus synchronous condensers. So I think there is different views of who will be ultimately the winner of that economic technical evaluation in the LT2029 tender, but the trend has been slowly towards a larger share of BESS in the UK, right? But that's not to say it could look different this time.
Yeah, absolutely. Okay. All right, folks. So we're pretty much out of time today, unfortunately. Should we just do one more quick question before we sign off, which I have now duly lost. Yes, sorry about that. So a question from Robert. So we talked about the competition with synchronous condensers. We talked about the essentially the competing applications potentially, and then we obviously have this existing paradigm of the grid in that, as Robert, so thanks for your question, Robert, points out, rotating machines supply instantaneous inertia support. And I'm not sure how true this is, but Robert posits that with battery storage and software, there will be a delay, first to detect the issue and then to respond. How long and what is the effect of this delay? So it's essentially, how closely can grid forming resources sort of mimic the roles played by those traditional thermal power generators? And so, Xiaodong, you want to go first on this?
Yes. I mean, the response time of inertia or reactive current of the grid forming BESS is instantaneous. I mean, there's also a specification from the NISU that when they certificate the grid forming performance, they require the response time to be less than 5 milliseconds. And we had a workshop with them and asked the reason behind. The answer is because it's a mimic of the virtual synchronous generator. You should have instantaneous behavior on the reactive current or active current injection into the grid when grid events happens. So we put a 5 milliseconds there to make sure your response is instantaneous, because 5 milliseconds means you don't have enough time for the detection. And the technology itself, I mean, what we are doing here, we are also really provide instantaneous response to the rock off or short circuit level, because you are voltage source. When there's a voltage difference on the grid, when there's a phase shift on the grid, the voltage and the phase difference between the two voltage sources generate the active power or reactive power directly. So we can't really see the delay from it. Yeah, that's it from my side. Thanks.
Excellent. Okay, thank you very much. So so Xiaodong, Michael, Sai, thank you so much for your time and expert insights into this topic. Certainly one that we look forward to both through Energy Storage News and our UK colleagues at Solar Power Portal. I'm sure we'll need to be on top of this, as we can see from the great questions still coming in. It's something that our audience, really wants to get on top of and to understand, grasp, and hopefully, I guess, grasp the opportunity both from an economic standpoint, but also, from an energy transition and grid modernization, and bringing us to a system fit for the future, and all of those things. So many thanks to our speakers, of course, to Envision for working with us on bringing these messages out. But most of all, of course, I would like to thank the audience for joining us, taking time out of their day to spend discussing and learning about this topic and asking questions on it. And we certainly hope that it will yield more fruitful conversations in future. And lastly, we'd just like to say, yeah, thank you all for being part of this fantastic, vibrant industry, which, as we can see, it's on every technical level is really exciting, and the potential of what it can do. With almost every big regulatory change that comes in, there's new levels of things that we are showing the world that can be done with some of these technologies. So yeah, for all of that, thank you so much, and we look forward to seeing you next time. Thank you, and goodbye from all of us.